INSEE is a proud member of the Siam City Cement Group Public Limited, a leading cement manufacturer in Southeast Asia. The Siam City Cement Group provides world-class construction materials to a host of countries around the world. This includes Cambodia, Bangladesh, Vietnam, Thailand, Indonesia and Sri Lanka. With a plethora of landmarks and buildings that define the skylines of these countries, the Siam Cement Group pledges to be a role model in corporate governance and sustainable development. INSEE Cement, Sri Lanka's premier cement manufacturer, is the brand behind our country's leading cement products and the driving force behind making Sri Lanka more sustainable. With a reputation built on outstanding performance in the quality of our products, unparalleled customer service, the dedication of our employees, our respect for the communities in which we operate, and our ambition to set the standards for the industry of tomorrow, we have contributed to the growth of Sri Lanka with iconic developments across the island. Just to name a few: the Lotus Tower, Altair Residencies, the Colombo South Harbour, Southern Expressway, Mattala Airport, the Kalladi Bridge, the Kotalavala Defence University, Mahinda Rajapaksha International Cricket Stadium. INSEE has cemented its position as the most preferred local manufacturer of cement in Sri Lanka, with its widespread distribution network comprised of over 7,000 dealers in retail segment located island-wide. Today, we have 2 plants in Puttalam and Galle and 2 terminals in Galle and Colombo. INSEE's Sunstar brand is Sri Lanka's first cement product to be awarded the Green Labelling certification by the Green Building Council and was the first blended cement to launch in Sri Lanka. INSEE has a wide portfolio of cements and services to suit all your construction needs. The most popular among them, INSEE Sunstar, INSEE Mahavali Marine Plus, INSEE Extra for mass pouring concrete, INSEE Rapid Flow Plus, INSEE EcoCycle, INSEE Concrete, Conwood by INSEE, state-of-the-art innovation and development facility. Having been a part of Sri Lanka for almost a decade, we will continue to build on our long heritage of shared loyalty, creating trusting relationships with our business partners, people and community, and delivering our promise of building the nation.
Ladies and gentlemen, good evening again. I think I'm very happy to see this much of audience and recipients today for the session. I'm Dishan Shamin, the sales manager for INSEE Concrete. And on behalf of the management of Siam City Cement Lanka Limited, I would like to put my gratitude to all the other organizers, including our management, Siam City Cement Lanka Limited. So I think INSEE Cement, even though we are a profit-making company and a cement player, building manufacturer, we have considered this kind of forums, knowledge sharing sessions, workshops. Now we have gone to the level of international workshops with this particular program. I think we consider this kind of activities as a key responsibility and a duty of us towards the nation. So sharing the knowledge and also the experience, not only the knowledge and the experience, but also the exposure is a key thing that we can contribute to the fraternity, to uplift the fraternity to the next step. So especially today, we are engaging some of the key stakeholder group is a young set of group, young engineers. So we are more than happy to work with them. I think that is the next level of development. Today, we are talking about Colombo's new set of skyline. It is not the same skyline, Colombo skyline that we have seen before a decade. So it's getting developed, not only Colombo, but also all around the country. Developments are happening. So the construction practices, the new innovative ideas, innovative approaches, and innovation has become key things in the development platform. So in that context, I think as INSEE, with a very comprehensive and a superb set of product portfolio, not only the products, but also the solutions. As a solution provider, not just as a cement or concrete or building material manufacturer, but as a solution provider to the nation, to the industry. I think we consider this as an activity based on our key, one of our key duties and responsibilities towards the nation. So I think with this program, with this session, there could be a lot of value additions to the stakeholders, to the audience. I think please enjoy the session, and I'm sure Dr. Moza will harvest this very healthy field. Thank you, gentlemen.
Knowledge is power. Knowledge shared is power multiplied. Ladies and gentlemen, very good evening to all of you. We are about to start the workshop on concrete mix design practice and cement use. I'm Dilni Kamge, the editor of Young Professionals Forum of ACSL. First and foremost, I warmly welcome the resource person of the workshop, Dr. Moussa Baalbaki, who is here to share his knowledge with us. We have especially organized this event to enhance the knowledge of young professionals. But we are very happy to welcome all the professionals who have joined us today. This workshop will be conducted in 2 sessions. In today's session, the objectives are to introduce the concrete mix design and to make you familiar with absolute volume method and to work some examples of practical use. In the next session, he will be talking about cement use. We will email you the date and time for the next session. And there's a good news for you. This workshop is recognized as a CPD course in local professional institutions in engineering, and it's totally free of charge. And another news, you can stand a chance to win a prize. Stay with us till the end. This workshop is organized by Young Professionals Forum of ACSL in collaboration with Sri Lanka Association of Institution of Civil Engineers, which is called SLAICE, and Association of Consulting Engineers Sri Lanka, ACSL, with our industrial partner, Siam City Cement. We would like to invite the young professionals to join with us in the Young Professionals Forum, which is also called Future Leaders. So I invite the Secretary of Young Professionals Forum, Ms. Rajita Gunatilaka, to explain the application procedure and to introduce the speaker. Over to you, Rajita.
Thank you, Dilini. Hello, everyone. I'm Rajita, the Secretary of the YP Forum of ACE Sri Lanka. Well, for those who have no idea what this ACE or this YP Forum is, it is my pleasure to give you all an introduction about the forum. ACE stands for Association of Consulting Engineers. It is the national body of consulting engineers in Sri Lanka, which is affiliated to the International Federation of Consulting Engineers, commonly known as FIDIC. This was founded in 1980 to promote common professional interests, and now it comprises more than 18 firms and have all of you as members. We will be having a lot of knowledge sharing sessions, not limited to contract related topic, but also many other areas in the field of engineering. So please don't miss a chance. It will only take a couple of minutes of yours to fill the form. And need to mention that there are no application fees to join the YP Forum of ACESL. Getting back to the session, the most important item of the day is awaiting. So it is with special excitement, I'm pleased to welcome Dr. Moussa, our guest speaker of the session. Speaking about Dr. Moussa, he is the former head of Advanced Concrete and Innovation at Holcim Technical Support, Switzerland, preceded by several positions in the areas of research and development, open innovation, advanced concrete technology, and concrete transfer. He joined Siam City Cement Lanka in 2018 as head of products and solutions portfolio. He has extensive experience in concrete technology and its constituents from production to product applications, coupled with holistic vision on cement, aggregates, and admixture technology. I'm sure the next hour is going to be quite fruitful for all of us. Dr. Moussa, you're warmly welcome to begin. Thank you.
Thank you so much, Ms. Rajita and Ms. Divini, for the welcome. Good evening, everybody, and I'm really glad to have this opportunity to somehow spend the next 90 minutes with young engineers, because I have been now in Sri Lanka for more than 2 years and a half, and I realize that this is the best place to develop technology because we have the most capable really engineers in the region. I can say that because you know, we are a global company in the region here, and we spend a lot of time with our colleagues, and they are requested to go and give support to Vietnam, give support to Thailand. Therefore, we are really proud of our engineers in Sri Lanka. Therefore, I would like to welcome you. The next 90 minutes, I will discuss about concrete design. Let me share with you my screen. Okay. Therefore, as it was mentioned by Engineer Delaney, that the topic will be about concrete mix design. Okay. Therefore, for that, I have 3 main learning objectives. I will just repeat them. The first one is really to, to introduce you the fundamental of concrete mix design for those who are not somehow familiar to concrete mix design, to talk about the fundamental, that is important. After that, to present you what we call the absolute volume method, because there is a lot of method of concrete mix design. But I mean, the basic one, the most important one, that if we master it, we are able really to go to the next level and very much understand mix design to satisfy performance requirement. That is very important. And last but not least is I would like that you are able at the end of this session to really design a concrete mix to achieve specific properties for a specific object. And for that, I have an example. It will be, for example, to design for the hotel terrace in Gold Face, a slab that is a reinforced slab. You are requested to design this reinforced slab. Okay, reinforced concrete slab. It is a 200 millimeter stick, exposed to airborne, but not in contact with seawater. Okay, that is important to mention. The specified characteristic strength will be 25 megapascal at 28 days on cube, and the slump requirement will be 15 centimeter, plus minus 25. Now, from the statistic, there will be more than 30 consecutive tests that are available, and the probability that the average of these 3 consecutive tests is smaller than the specified of characteristic strength is 1% with 2 MPa standard deviation. I just started with this slide because I want you to see already from the very beginning what you could expect for the next, let's say, hour and a half. That will be really the objective here. Is I would like that at the end of this session, that you, for those who are not used to concrete mix design, they will be able to translate all these requirements in a specific concrete mix. Okay, that is really one of the most important somehow learning objective for this session. Now, if you talk about concrete, I mean, concrete is a very simple, but at the same time, a very complex material. It is simple because very often people, I would say, abuse from the simplicity of concrete, because when you look the ingredient, with 4 simple ingredients we can find somehow in the nature, the aggregate, the sand, the water, and the cement that is processed, you can produce a concrete where the range of compressive strengths can go from 1 megapascal to 100 megapascal. You see, this is really what is really important here to say. It is simple, yes, but the technology content is very important. Okay, I just try to do some analogy. You have a flour, good quality flour. You can give it to one person who will make very nice bread, very tasty bread. Another one, it will not be exactly what you expect. Therefore, the difference will not come from only the ingredient. The ingredients are important, we will see it. But what is important is really the technology content. Okay, therefore, it's not as simple as very often people think. Therefore, a concrete mix is not a concept of I have done it before, I can copy paste it. That is not the concept we should use. Now, the most important thing to consider also that the objective of designing the right mix is really to determine a compromise between economical and practical combination of readily available material. Because it's a very, the system of concrete, how you say, you have to really work with available raw material. Okay? Sometimes you have some issue that has some implication. For example, we can talk in Sri Lanka, not only in Sri Lanka now, about the sand. We have more scarcity of good quality sand. We use very often, let's say, quarry dust or manufactured sand. This has some implication, but there are always opportunity with that. You see, as an engineers, we know it very well. There is always solution, and those solutions very often need to be taken into consideration by using local material. That is important for me. As an engineer, I will never accept, I will never try to get, for example, aggregate from Australia to produce a 100 megapascal concrete in Sri Lanka. I will not do it. It's okay. And also, I would like to say, I'm one of you, I'm an engineer also. Very often, many engineers do not feel very comfortable with matters that cannot be reduced an exacting set of numbers. Because we like models, we like mathematics. Everything need to follow some law. But very often this is not the case with concrete. This is why concrete is a mix of something that is empirical, but at the same time that has a certain also technology behind it. Okay, this is why very often some engineers they don't feel very comfortable for that. And this is why I'm really proud, I'm very happy to have this opportunity to spend this couple of minutes with you to discuss about this topic, okay? And again, as I said, I would prefer really to have you in a class, to have you in our innovation to industry somehow plenary room where we can have a more like face-to-face discussion, and I hope that in a very near future, we will have this opportunity where we can dig further, this topic if it is really relevant for you. And I'm sure that is really important because as Dishan, he explained that today Sri Lanka is really going to grow with infrastructure, with large infrastructure project, with really state-of-the-art design. Therefore, we need to introduce technology. We need really to take somehow all what we know as engineers and really implement it, okay, for the sake of having a better future, a better Sri Lanka. It's okay. Therefore, designing concrete, that satisfy performance requirements, I have here really 6 that are the most important one. Workability, what I mean by workability is how easy I can place a concrete, and very often we talk about slump. I will show you according to EN standard, there is other way to express workability. Also the placement, we can consolidate concrete in a different way. This is why very often when we design the concrete, we should understand already upstream, before the concrete arrives downstream, we should understand how the concrete is going to be transported, how it's going to be placed, and how it's going to be consolidated. These are really important because very often if we don't take this into consideration, I like workable concrete, but if I place my concrete and I know that it will be highly vibrated, I can have segregation, I can have bleeding problem. Therefore, this is all important to take into consideration, okay? After that, the strengths. Okay, as an engineer, we know this is one of the most important engineering properties, okay? When we talk about structural stability, mechanical stability, we talk about compressive strengths, okay? And this is really the strengths of concrete. When we look concrete, when I look all the engineering property of concrete, concrete has a lot of future advantage and benefit, okay? Probably one of the weakest point of concrete is its tensile strengths, okay? That is why we put reinforcement, but when we look to the strengths of concrete, as I said, you can design easily concrete up to 100 megapascal, okay? One other aspect that is important to satisfy performance requirements is really the aspect of durability. Okay, the aspect of durability, it's really important. Aspect of durability is important because very often we miss this important aspect because when we design, it has to last. Okay, it has to last the intended use of the structure. For example, if I build a bridge for 50 years, I don't want that after 25 years, I need to repair the bridge. This has a very high social cost. Today, most of the bridges all around the world are even designed more than 75 years to 100 years. Okay, that is why the aspect of durability has to be taken into consideration. We will see it. After the appearance, the color. As an architect, I start my study in architecture, and with concrete, we are able really to give more feature for building. Okay, if we take, for example, fair face concrete surface, we can have warm color, we can have cold color, and concrete is the best material for that. You see, for example, in this example, this is a school of architecture in Marne-la-Vallée in France. Therefore, you see a fly ash on your right side and slag on the left side. Okay, that's beautiful, that gives volume, okay? And in terms of aesthetic, I would say that nobody will say that this is really kind of art, okay? Also, what is important is the economy part. We have to be cost effective. Of course, we have to be cost effective. But I would like also here to mention something that is very, very important. We are a consumer. I will go tomorrow, I will buy, for example, a TV, and they will give me latest technology, and they will give you maximum 2 or 3 years of guarantee. Okay? If I buy the best tire for my car, okay, the Pirelli, the whatever you want, state-of-the-art tire, okay, the guarantee is maximum, again, 3 years. Okay, I will pay for one tire, I will pay about $100 US. That will last, this is the last technology, will last 3 years. When we take concrete, for example, okay, if we design correctly a concrete can last minimum 50 years. Therefore, concrete is a very noble material for engineers. Okay, and when I say 50 years, this is 50 years for a cubic meter that will cost you less than $100 US. It's a 2.5 ton of different materials, okay, that will last 50 years, okay? This is why if you look around you today, schools, our house, our universities, our hospital, whatever you look around you is built with concrete. That is really one of the main advantages is the economy. Okay, that is why the next best alternative to concrete stays concrete. There is no next best alternative. Today we talk a lot of hybrid system, okay, but still the cost is far more expensive than concrete. Even though I can bring other elements here that I don't put it, for example, when we talk about safety, fire resistance. I always give the example, for example, if you take the World Trade Center in New York after the terrible, terror attack. If this World Trade Center, the twin was concrete infrastructure, concrete structure, they will still be there. They were built steel, therefore, fire, they collapse. That's really something that you as an engineers, okay, sure, you see all these future advantage and benefit. Therefore, you see, concrete is much beyond the 25 or 30 or 50 megapascal. Therefore, that is what I want to ask you, that try to be not too prescriptive. Try not to be too prescriptive. In front of you, you have challenges. You need to build sustainable performing infrastructure. Sustainability becomes a very important element in the concrete mix design. Okay? Therefore, you have to think, where are the solutions? Therefore, you need to think performance-based and not prescriptive-based. Now, in terms of method of proportioning, you know, when we design a concrete mix, it involves the following: the establishment of specific characteristic. That is important, as I said, in terms of strength, in terms of workability, all this aspect we discussed, okay? Intended use, the aspect of exposure condition, you know, and also the selection of proportion of available materials with the greatest economy. You see, I mentioned available material. Therefore, that is very important here. When I talk about availability of material, therefore, you see today we are more going toward circular economy. And when I say circular economy, we are not anymore dumping. We cannot anymore afford to dump end of life of material. Therefore, concrete, again, when I come to available material, the second life of concrete is a great aggregate. Yes, it's a great aggregate. Therefore, you see, this is an issue. The implication is if we dump it, we are going to create a big mess. Therefore, the opportunity is to take this end of life of demolished concrete, turn it to aggregate, for example, and design a concrete taking this recycled aggregate. This is just an example. Therefore, that is why it's very important that we are creative, we are innovative, we look what has been used in different countries, in different projects, okay? And try really very fast to implement it in our country. That is important. And also, there is, as I said, there is different numbers, different method for proportioning concrete mix. But I would like really to focus on the basic one, that is the absolute volume method. Because if you master the absolute volume method, you will understand all other, okay, designing of concrete with more sophisticated element on it. But if you know the absolute volume method, I can guarantee you, with my more than 25 years of experience, you know, you have more than 90% of the knowledge you need, okay, to design without any durability problem 50 years concrete. It's okay. Therefore, the method of proportioning, absolute volume method, is very simple. Everything is transformed to cubic meter is made for 1,000 liters. Therefore, you have your constituent, you have the cement, you have the aggregate, you have the water, you have the sand content and a certain porosity. Okay? I'm not talking about admixtures here. I will come to the part of admixtures, okay? Because admixture, the volume is very, very low. But if I take, for example, the big volume that I have in my cubic meter of concrete are these five somehow constituent, 4 constituent plus the porosity. If you know the bulk density of each of them, if I divide the mass by the density, I will have my volume. And if I sum up all this, I should get my cubic meter. Okay? Okay. That is important here. I would like to make a small break for you, because when I call my ready-mix guy and I ask him concrete, I will never call him, I will tell him I need 2 tons of concrete. You agree with me? I will tell him I want 2 cubic meters of concrete, therefore it's volume. But of course, in some steel segment, if I take, for example, the individual has builders, the what we call the retail segment in Sri Lanka or in a lot of countries, okay? We still see people, when they mix on site, they mix volume batch. They don't wait. They go volume batch. That is why I would like to say that it is very important at the end, if you want to compare apple and apple, as an engineer, I want to really compare one mixed design to another mixed design. I need always to bring back all the constituents per cubic meter. That is important, okay? Because we compare cubic meter to cubic meter. That is important, okay? This is one thing that I would like that you keep in mind. Therefore, if you, for example, are working on a job site where people still take 1 part of cement, 2 part of aggregate, and 2 part of sand, and 4 part of aggregate, and they do like this, adding water, now you need to understand, okay, what is really that mixed design. And we will see later when we talk about compressive strengths, when it comes to statistics, why very often we really over design those type of concrete. Now, a concrete, as I said, we express everything per cubic meter. Therefore, if I have, for example, 1 cubic meter of concrete with aggregate, with sand, with cement, with water, each of them will occupy a certain volume. Okay, like say air will have 6% of air. This will be 60 liters. Okay, water 150 liters. Knowing the density of each of them, I can get the kilogram per cubic meter. Therefore, I can get really for 1 cubic meter of concrete the constituent kilogram per cubic meter. Therefore, always when you are somehow designing a concrete, you should come up at the end with kilogram per cubic meter. It's okay, that is important. Now, selecting a mixed characteristic, okay, therefore you have to take into consideration the intended use of the concrete, okay, that is one aspect, and the second one is the exposure condition. These are 2 important elements that you should consider. The intended use, and second, the exposure condition. Is it a house? Is it a bridge? And where is this house? Is it in Kandy or is it in Goldface? That is important. This is what we talk about exposure condition. And last but not least, the size and the shape of the concrete element. Because in concrete, you have constituent with different sizes. You start with the smallest, that is the cement. In the webinar number 2, we'll talk about cement. If I take average size of a cement is, let's say, 10 micron. 10 micron. But if I take the maximum size of aggregate is 20,000 micron. You see, from 10 micron to 20,000 micron. Now you have to put all this together and have a concrete that has a good cohesiveness, that when you mix it and you place it, you don't have segregation and you don't have bleeding, separation. That is really exactly why it is very important to master the basic. That is where we will start for. Now, this is why we will go through what I call the important steps. We start with step 1. As an engineer, I need to know what is the strength requirement. This I cannot invent it. Okay? I should know the strength required according to the design. After that, there is one important element, that is the water cement ratio. Because there is a law, a very simple law in concrete technology, up to 50 megapascal. There is a linear relation, they call it the Ferré relation or the Abraham relation, where the water cement ratio, okay, is linear with the compressive strength. Okay? When you reduce your water cement ratio, you increase your compressive strength, or when you increase your water cement ratio, you reduce your compressive strength. Therefore, it's almost linear. And there is no universal one. Will depend to the raw material. Cement, aggregate, sand that you are using, and the mix. Okay? After, the coarse aggregate. You see, coarse aggregate is not inert. Coarse aggregate play a very important physical role in the concrete, because coarse aggregate will occupy a big volume of your concrete. Almost, I would say, 40% of the volume will be occupied by, even sometime more, by the coarse aggregate. Okay, after the air content, because concrete can be with entering air or without entering air. In Sri Lanka, we do not enter air, we have entrapped air. But if you go to country like Switzerland, because we have winter, we need to protect concrete from frost. Therefore, we engineer. Okay? Therefore, this topic we will not discuss about here. The workability, which slump I need. I'm going to pump the concrete, I'm going to shovel it, I'm going to bring it with a crane. That is all important aspect. Just a moment, looks like the sound is not clear. Okay, sorry, I will, thank you for, sorry, I have to go back. Yes, please you tell me if it is still not comfortable, the sound, okay? Therefore, after that we have, knowing the workability, we have to know how much water I should add in my concrete mix, okay? Because yes, water is a very important ingredient because water will hydrate your cement. This we'll see in the second webinar. But at the same time, if we put too much water, it's not good for the concrete. The cement content, okay, how much cement I should put, this is important to know. The cement type, there is different type in the market. Therefore, it's very important to understand why we have different type of cement. There is a good reason for that, okay? Admixtures, okay, it's important also when it's possible, when it's available to use, for example, water users, or we call them super plasticizers, okay, because those admixtures will help you to reduce the amount of water. That is very important to take into consideration. And at the end, when we go from step 1 to step 9, we are able, okay, to fill what is left in the cubic meter with the sand. Okay, therefore you see these are the 10 important steps, and after the 10th step you do what you call the moisture correction. Why I say moisture correction? Because if you go to the job site, if you look sand or aggregate on the piles, very often they are not in what we call saturated superficially dry. Therefore, it's not really saturated and superficially dry. Therefore, they are wet or they are too dry. Therefore, you need to do a moisture correction to assure that you have always a mixed design with the same water cement ratio. Otherwise, if I do not consider the moisture correction, if my sand, I have, for example, 800 kilogram per cubic meter of sand, I make a mistake of 1% with my moisture because it was raining yesterday, okay? Suddenly I will bring 8 liters of water more in my mix. You see, this has a very big impact on the properties after of the concrete, before you go to the dry mix. Okay, these are really the steps. I will go through it with you and to see how to, to answer to each of the steps. When it comes to first step, strengths, okay, therefore you have two considerations for the strengths. You have the structural design consideration. The structural design, this is really by the engineer who will design this, depending what you design, is it a 10 stories building, is it 1 story building, you have to design, and you have the structural design requirement, and the durability consideration. When I say durability consideration, this is really the exposure condition. Is it a slab? Is it indoor slab? Is it outdoor slab? Okay, is it a bridge? Is it a bridge in the mountain, in area, or is it a bridge in gold face? This is all important to know, okay? Therefore, even though we say durability of concrete is not directly related to strength, still, strength is used as a kind of indirect means of assuring adequate durability, okay? And I hope that we are able in the very near future, you know, to have a session in our innovation to industry collaboration space in Peliagoda, where you will see that we have a special room, we call it durability space, really to assess the direct, and not the indirect, but the direct, okay, durability indicators. Corrosion, permeability, carbonation, whatever is in terms of durability, you have a direct measurement with a state-of-the-art equipment, okay, to allow you to take into consideration this durability consideration, okay? Now, we are going, I would like to really give you some insight when we go to these 12, I say, steps. What the EN206 concrete that is used in more than 33 European countries and a lot of also many other countries, about concrete specification, performance, production, conformity, and also the building code of requirement for structural concrete. This is the ACI 318. This is really used in most of the Anglo-Saxon countries, including, a lot of many other countries. Okay, therefore these are the two. If I look to Sri Lanka, we are a lot somehow inspired by the European standards. Okay. But at the same time, I see also more and more projects where the ACI, okay, the American Concrete Institute standard also is somehow used. Therefore, when it comes to the 206, how we design, what are the elements we need to specify to let the producer, okay, for example, in say concrete, to fulfill the requirement of the engineers, of the contractor who is requesting. Therefore, the EN206 will give you some indication how to design the concrete with a service life at least 50 years. Normally, you should go up to 50 years without having major intervention in terms of repair or rehabilitation. Of course, you can go above 50 years, okay? But at least what we will see today, up to 50 years, you should not have any problem if you follow the different steps. Now, you have first the class of compressive strength. You see, strength is important. And when I design a concrete, this is the most important, I say, engineering property is the strength, which is the class of compressive strength, which is the compressive strength. Second is the class of consistency. When I say class of consistency in terms of fresh concrete properties, for example, in Sri Lanka, which slump I need, that is important, I should specify, okay? The third one is the class of chloride. The class of chloride, because you can have a concrete exposed to chloride like marine, okay? It could be even not marine. You can use also chloride to melt the snow in the mountain, okay? This chloride can somehow, to a certain extent, okay, have a certain negative impact on the corrosion. But at the same time, in your concrete, okay, you have to also limit the amount of chloride. And we will see, for example, 0.1%, very often it is used, to 0.4, depending if the concrete is reinforced, if it is post-tension, therefore the class of chloride content is defined in the standard. Now, very important is the class of exposure. The class of exposure, this is very, very important here. Because when I design the concrete, I should know, okay, during the lifetime of the concrete, what kind of exposure this concrete is going to withstand. Is it going to be wet always? Is it going to be always dry? Or is it going to go through different cycle of wetting and drying? Is it going to be exposed to chloride, to carbonation, to CO2, to sulfate, whatever it is? Therefore, it's very, very important to consider this aspect in the concrete design. Last but not least is the maximum size of aggregate. Okay? Here again, in Europe, according to the 206, when I call the ready mix, I have to specify these 5 boxes. I should tell him is a C2530 concrete, is a S3 class of consistency, is a chloride 02, is a XC4, for example, and the maximum size is 32, for example. Okay, therefore you have, and therefore the producer will take this input and you will translate it in a concrete mix design. Okay, and that is what I would like to do with you. Now, when I take the exposure classes, okay, the exposure classes, there are 6 exposure classes according to the EN206. You will see when I look to the ACI, okay, the American ACI is similar. It's not exactly the same, but it's very similar. Therefore, you have when there is no corrosion, or the risks, this is X0. Very often these are for lean concrete, or for some foundation, okay, where the soil is not contaminated, it is not reinforced, okay? Therefore, in this case, it's okay, we can go for X0, okay? XC is when you have problem with carbonation. It means if your concrete is going to face an environment where soluble CO2 can enter to your concrete and carbonate your concrete. We will see this. Okay. After that, this is a corrosion. The second mode of corrosion will be XD class. The XD class is when you have chloride, but chloride that are not coming from, for example, XC from the seaboard. Because chloride, as I say, we can use the icing salt. It can be also a byproduct from an industry. Okay? Therefore, chloride can come from there, but also chloride can come from the sea. Therefore, you have a different, like in Switzerland, we don't have sea. Therefore, the XS do not exist in the 206 with the National Amendment of Switzerland. Okay? But if I go to Spain, they have XS because Spain has the somehow the Atlantic, sorry, not Atlantic, the Mediterranean Sea. It's okay. After that, you have frost. In Sri Lanka, we don't need frost, but if you go to country like Switzerland, if you go to country like Canada, you know, they have winter. Therefore, you have a lot of cycle of freezing and thawing. And also they use the icing salt to melt the snow, for roads, for example. Therefore, you need to take this into consideration. Last but not least is the chemical attack. Chemical attack from the soil, from the groundwater. It's very important to see, for example, if you have some acidic attack, if you have some sulfate, these are all very important, okay, to take into consideration. Now, I am not going to go through all of them. I will just, for example, consider the XS. The XS, but if you understand the XS, you will understand all the rest, because I will show you a table, they are all based on that. Now, I will not go too much in deep, and even though because we will not have time to explain the mode of deterioration of each of these exposure classes. This could be another topic. Okay. Now, when I take, for example, the XS, this is chloride from seawater. Okay, we have three classes: the XS1, XS2, and XS3. Okay, XS1 is really when the structure is near or on the near the coast or really on the coast. Example, Goldface for Sri Lankan people, because I know there is some participant from abroad, from India, from Korea, from Malaysia, I don't know from where also. But here in Sri Lanka, for example, we have Goldface, for example. It's a very beautiful avenue and is facing the sea. Therefore, all the building, all the somehow the concrete that has built in the area of Colombo need to consider a minimum exposure condition of XS1. XS1, okay? That is important. Second one is when the concrete is part of a structure, either it is permanently submerged or in the tidal zone. Can be a bridge, for example. Therefore, if it is permanently submerged, you take the XS2. Okay, and if it is in the tidal zone, or spray zone, you take the XS3. Okay, therefore you see, it's not about being, I say, chloride from only seawater. It depends where is your element. Now, you see, there is some recommendation. Okay, this is recommended in the EN 206. Okay, it's not mandatory, but it's recommended for it's good as young engineers that when you start to design your concrete, this is a very interesting table. Okay, there is more than 25 years of back experience that is backing this table. That is very interesting because you can use it. Okay, therefore you see, if I take XS, for example, it will be the same for carbonation, for chloride other than seawater, for frost, for aggressive environment, like for example, when we have sulfate, all this stuff. Therefore, if I take, for example, building in Colombo, minimum those buildings should be XS1, minimum XS1. Because you remember we say XS1 structure near or to on the coast. Exposed to airborne salt, but not in direct contact with seawater. Even if we are at 25 kilometers from the coastal, therefore I will say Colombo and the big Colombo, normally all the concrete need to be designed minimum with XS1. This means water cement ratio should not be above 0.5. Therefore, you see, 0.5, this is one condition. And we are talking about strengths. Therefore, you cannot design with less than 37 megapascal. Even though from a structural point of view, you can design 25 megapascal is enough, okay? Due to the fact that you have exposure condition, okay, with a certain severity, okay, you need to increase your design to 37 megapascal, okay? Therefore, that is, we are talking about the same thing. You have different, like if you go, for example, to XS2 and XS3, this is either submerged in water or in the splash zone. You see the strength is 45 megapascal. 45 megapascal, yeah? Even though probably 35 megapascal will be enough or 30 megapascal will be enough. But this is not the case, huh? You have to take into consideration the exposure condition. Therefore, now, if I take the ACI, you see, they have 4 exposure classes. They don't have 6 because they already include in each of the classes what we have in the European standard, the X0. That is what they call F0 for frost, S0 for sulfate. That is our XA. This is our XF according to the European standard. This is in contact with water. Therefore, for water permeability, they have W0. This we don't have it directly in the how you say our EN206, but in the EN206 we have the XA. The XA is also all related to permeability. Therefore, it's similar to the XA. After you have the corrosion here, they have only one category, call it C. C0, C1, C2, and in the European standard there are 3. There are the XC for carbonation, corrosion due to carbonation. You have XS, corrosion due to chloride from seawater, and XD, chloride not from seawater. You see, that is the difference. The second difference is that if you take ACI, if I have to design, for example, a slab, I need to take the worst condition all the time. I should consider what is the apply for frost, what is the apply for sulfate, for contact if it is in contact with water, and in photo corrosion. Okay? For example, this will be F1, S1, W1, and C2. After that, I see what is the worst condition. I design my concrete according to the, in this case, will be C2. That is how they design. Okay? Therefore, the engineer need to consider all of them and take the worst case scenario. Okay? Therefore, they have also, you will see they have also limiting value, exactly like in the EN. Okay, what they don't have is a restriction on the cement content. In the EN, in the European standard, you have the minimum cement content. They have the minimum cement content and the maximum water cement ratio and the minimum compressive strength. In the ACI, they put only requirement on the maximum water cement ratio and the minimum strength. They don't put restriction on the minimum cement content. It's okay. That is really, I mean, the big difference. Now, of course, at the same time, as an engineer, when you design, therefore the required strength should be equal to the specified. Therefore, if I'm specifying 30 MPa, okay, I have to take an allowance to take into consideration variation in materials. This is why, if you buy a concrete, you need to buy a concrete from a producer who has a very good quality assurance system, with a very good standard deviation, okay, with enough number of consecutive tests for the mix, okay, he is developing for your project. That is important, okay? Therefore, you have to take this into account. For example, in Sri Lanka, whenever you design 30, you request 40. I will explain why, okay? Therefore, that is important because you have, this is, for example, the normal distribution, okay, for standard deviation. With standard deviation, therefore, if you specify, you have to add, okay, for the design say, you have to add a factor K multiplied by the standard deviation. And this factor K, if the number of tests, consecutive tests, is more than 30, equal 1. Therefore, a professional ready mix normally, okay, he will just add the standard deviation because the K number should be 1 for him. Okay, now, according to the ACI 218, if you look at the Sri Lankan cases, you will have also very, very similar, you know. If the concrete, for example, is below 45 or above 45, you have condition. okay, where the required strength will be specified plus 1.35 standard deviation or this equation. Okay, depending if, for example, the probability that the average of 3 consecutive tests is smaller than the specified strength is 1, therefore you take this relation. It's okay, therefore that is really important. And now, if you don't have 30 consecutive tests, you see 30 consecutive tests and more, the K factor is 1. Now, if you have only between 15 and 29, depending to the number of tests, less than is higher is the K factor. It means if I have 50 megapascal, it should be already 55 plus the standard deviation. This is why very often we go to worst cases when we don't have a good statistic or good quality assurance system. Therefore, designer or specifier or engineers, they go with the maximum of, let's say, of security. Okay. Unfortunately, this has a certain cost, but this is how it is. Now, if it is less than 15 consecutive tests, this is, for example, really when you don't have, for example, data, the bad market, they don't have data. Therefore, in the bad market, if I design a concrete less than 25, I have to add 7 megapascal. If it is 25, I should design 32 megapascal. This is why if I look cement utility factor in the bad market, is cement utility factor is how many kilogram of cement I need to get 1 megapascal. Normally in the ready mix operation, we need less than 10 kilogram. We are around 7, 8 kilogram per megapascal. But if I go to the retail market, for my 20 or 25 megapascal, very often I need 13 kilogram. You see, I'm wasting minimum 3 kilogram, okay, per megapascal, okay, just because the technology content I'm using is not the optimum one. You see, that's really, it's not about the cement. Very often people discuss very much about the cement. No, I always say it. You give me any type of cement, we can produce 1 to 100 megapascal. The difference is the technology content plus exposure condition. Why we have sulfate resistant cement? Why we have cement for more durable concrete? There is a reason behind that. Concrete, for example, that need to be bleedless, concrete that has easy to place, you know. Also, do you design differently this type of cement than concrete that is doesn't need to have this type of properties. Therefore, this is for the strengths. Now, when we come to the determination of the water cement ratio, okay, the determination of the water cement ratio, here you should take the lowest value that is required to meet either the required strengths. For example, I design my slab, I need 25 megapascal. Okay, but if my slab is exterior slab, I have to take durability consideration, and suddenly is not 25 megapascal, but is 38 megapascal. Therefore, I need to consider the water cement ratio that is the lowest to achieve the required strength or the durability consideration. Now, important remark here that within the range of within the normal range of strengths used in concrete construction, compressive strength is inversely related to water cement. This is what I said, that you have a very good relation between compressive strength and water cement ratio. That is very, very important, that we need for a set of constituent to have this kind of relation between compressive strength and water cement ratio. Also, the strength and durability are governed by the quantity of mixing water used per unit of cement. This is why I say, you know, very often people put too much water. Therefore, if you have some negative effect, not because it is sometimes the cement or it's the aggregate or no, because you put too much water. And difference in strength for a given water cement ratio may result from the aggregate. Yes, if you don't have sound aggregate, you have a flaky, you have a really bad shape, or the type of cement, you use low, like 32.5 strength class instead of 42.5, for example. If you don't use mineral components, for example, you don't develop enough strength. If you are entering air, if I have 2% or I have 5% of air, it's not the same. Okay? Because more I put air, I will lose strength. Use of admixtures, I can use some admixtures, and in this case, I can really reduce my water cement ratio. And the length of curing, strengths develop with time. Okay, and why we are sticking on the 28 days? Because we are used to work with OPC. When a lot of technology was developed with concrete, it was the time where OPC, and we know OPC, you develop at 28 days almost more than 80 to 90% of the strengths. But if you take, for example, a composite cement, if you take what we call blended cement, therefore those blended cement, they develop their strengths, they continue to develop their strengths up to 1 year. If you look the 56 days, you look the 90 days, okay, of a concrete produced with blended cement, okay, or Portland limestone cement as a ternary system, you see the strengths continue to gain with time. And in the case of PC, will be flattened because you have developed the maximum of the potential coming from the clinker. Therefore, this, you have to take this also into consideration. Now, this is a table, for example, where you see for 28 days compressive strength on cube. Okay, even though I took this from the ACI, but I translate this number for cube. You see, for example, if I have to design a 30 megapascal concrete, okay, I can work with 0.61 water cement ratio. Now you understand in Sri Lanka, for example, very often when the people design for bad market, when the people go for 20 megapascal or 25 megapascal, if you do the real calculation of the water cement ratio, very often they are above 0.65. Because yes, of course, you get this compressive strength, but the durability of those concrete is very low, as you could see in the exposure condition. Therefore, if I am producing a concrete with water cement ratio above 65, you will see it in the EN206. These are all concrete, what you call lean concrete. These are not for structural concrete, not for concrete with reinforcement. Because the maximum you can go is 0.65. Therefore, as soon as in the bad market, a concrete gang leader or these people who produce the mason concrete and they add water and they go to 0.7, you test, you have 22 megapascal, you are happy, but you should not be happy. Because corrosion will take place within the 20 years if your concrete is exposed. Okay, that is really, you should keep this in mind. This is really important. Now, you see, exposure condition, if I take XS1, 0.5. This is, I cannot go above 0.5. Now, you see X0 here, I do not have any requirements. As I said, no risk of corrosion or attack. This is lean. Okay? But if I look all the maximum water cement ratio for exposure classes, the maximum will be 0.65. That is quite high. You agree with me? That is quite high. That is the water cement ratio. Normally, we should never go above that. Because as soon as you are above 0.65, you have a problem with really percolated porosity. Your porosity is percolated. I can produce a 25 megapascal, dense, good permeability, another 25 megapascal, very permeable. Therefore, that is exactly what we should keep in mind. This is why those tables exist. It's not perspective only. It's not on compressive strength only. Okay? Now, step 3 is the coarse aggregate requirements. The coarse aggregate requirement is important here because you need to consider the gravity, the nature of the particles. That is important if it has the shape, the porosity, the particle size distribution, the particle size. And at the same time, we should keep in mind that when you have a coarse aggregate graded up to the larger size, practical for job condition, that provides the most economical mix because around 75% of concrete volume That is a lot. Therefore, it's very important that you optimize your concrete mix design if you want, for example, to reduce shrinkage cracking, for example. First things, you optimize your concrete aggregate content in your concrete, because the aggregate will never shrink. Okay, this is the anti-shrinking component in your concrete. But if you reduce your aggregate, you increase the volume of paste, the concrete will shrink. And also, it has an influence on the workability and the water demand, the coarse aggregate. So you have to find out the optimum. We will see what is the optimum. And at the same time, I want to say that when you design high-strength concrete, okay, it's better to go with a smaller size of aggregate. Because in high-strength concrete, very often the amount of fines content in your mix is high. You have more than 400 kilograms of cement, because you are heating more than 70 megapascal. Therefore, your specific surface of the coarse aggregate, if it is increasing, is not a problem. Because when you reduce the coarse aggregate size, you increase the specific surface. But it's not a problem because you have enough paste. Your cement content is high. Okay. Therefore, also you have, depending your reinforcement, distance from the reinforcement to the edge of the mold, distance between two reinforcement, the size of the concrete, if it is on grade, if you have to pump the concrete. These are all information that you need to consider for the maximum size of aggregate. For example, in the slab, for example, if my slab thickness is A, the diameter, maximum diameter should be 1/3 of the thickness, maximum. I cannot go above that. Or if I'm pumping a concrete, should not be more than 1/3 of the diameter of the hose. And never more than 37.5 millimeter. Anyway, nobody will pump. In Switzerland, we can pump even a 32 millimeter aggregate. Okay? Therefore, just for you, this is the third element that we need to consider. Now, there is one important also a factor that is important from the sand, that will tell you how much coarse aggregate you need, is the modulus of fineness of the sand. Okay, if you take the EM, the European countries, they do not use very often the modulus of fineness of the sand. Okay, but if you look the ACI, okay, the modulus of fineness give you to understand how fine is your sand. Okay, and normally for normal concrete, between 2.3 and 3 modulus of fineness is a good numbers. Okay, therefore, when I say that, it's important because if I have a fineness modulus below 2.3, it means my sand is too fine. It's too fine. And, or if it is more than 3, it means the sand is too coarse. Therefore, if you cannot increase the cohesiveness of your mix, suddenly you have a problem of bleeding. For example, if I switch from natural sand to, crushed sand, like quarry dust, and if my modulus of fineness from natural sand, that is normally around 2.6, and I'm above 3, 3.1, 3.2 for quarry dust, suddenly I miss, okay, a certain cohesiveness, and I can have more bleeding. And you can experience that if you go, you walk around, you go to job site, okay, and you will see it sometime, okay? Therefore, modulus of fineness is very simple. You have your ceiling, you have your opening, percentage retain, you get the cumulative passing the sieve, and you get the cumulative retain. If you add between the 475 millimeter and the 150 micron, if you add all this number and you divide it by 100, this is your fineness modulus, 2.83. Very simple. But this is a very important characteristic, okay, of the sand, because you will see next slide. Based on this one, I will know how much coarse aggregate I can put. The second important element is what I call the dry rolled bulk weight of the coarse aggregate. Okay, if I have a coarse aggregate with different aggregate with different shape, flakiness, elongation, or a better form, or a different grading. Okay, if I take a container, a bucket of 10 liter, and I fill this bucket and I compact it in 3 layers, okay, I weight it, better is my grading better, more favorable is my aggregate shape, higher will be my dry eroded bulk density. Okay, therefore this is a good indication that is integrating, physical aspect of the coarse aggregate. That is very interesting. Sometimes you can go down to 1,550, you can go up to 1,700, 1,800. A favorable coarse aggregate, you increase this value. Okay, considering the same from the same, from the same rock. Okay, from the same parent rock. Okay, you have a standard for that is the ISM C29. Now, you see, this is a table that gives you what we call the bulk volume factor for the coarse aggregate. What you have in green here is the fineness modulus here. Therefore, you need to know the fineness modulus of your sand. I know it. Now, I should know the maximum size of aggregate. I know my maximum size of aggregate. Therefore, if I take, for example, an example, 25 millimeter aggregate with a fineness modulus of 2.8, I have the bulk volume factor of 0.67. Now, this 0.67, I will take this factor, I will multiply it by the dry eroded bulk density. That is 1,650 in the case we have seen. Therefore, in my mix, if I take this sand and this specific aggregate, I can go to 1,105. Sometimes I cannot go more than 1,000 even. Okay, this is why this factor is very important. Therefore, we know now how to get the amount of coarse aggregate. Okay, and so you have to keep in mind that if you have to pump concrete, okay, you have to reduce very often 10% of coarse aggregate, or if you have a slip form, you increase by 10%. Okay, therefore that somehow there is some also recommendation in your in the standards. Okay, and also by practice we know that. Now, air content. As I said, very often you have to entrain air, but in our case we do not entrain air in Sri Lanka. Therefore, we do not entrain air, or in India or in any country in this region here, we do not entrain air. Okay, because we don't have frost problem. Therefore, only if I go North India probably. Now, if, for example, I take the case in Sri Lanka between 20-25, okay, millimeter coarse aggregate, you see I can consider between 1.5 to 2% of air in my concrete. Of course, every concrete will have a certain volume of air. That will be like entrapped air. Okay, that is really what we can consider. But for example, in severe frost condition, for example, Nordic countries, they can go up to 6% of air if they have this type of coarse aggregate maximum size. That you can have almost 4 times more air, but this is not entrapped air, this is entrained air. It's totally different. This you use admixture to entrained air. Now, workability requirement, here also it's the ability for the fresh mix to be transported, placed, compact, and finished. We remember about the 6 requirement. This is a very important requirement. Otherwise, you can really somehow produce a very good concrete mix, but when it comes to place the concrete, when it comes to finish it or to consolidate it, okay, the condition are not favorable. Okay, therefore the slump is indicative of workability when assessing similar mixture. That is somehow, this is why we use, for example, the slump test. Now, in the EN 206, okay, there is 3 different ways for normal class of consistency. There is what you call the S class, like for example in Portugal, in France, in Spain, in Sri Lanka, in India, but in India will be different because in India they compact the coal here in 4 layers. All other countries like Sri Lanka, we compact it in 3 layers, 25 times. In India, they will compact it in 4 layers. Therefore, the numbers are not the same. For, let's say, 115 meter in Sri Lanka will be different than 115 meter in India. This is why I always say it's really important. When we compare numbers, you need to be sure that the numbers are comparable. So you see, you have different class of consistency, but as we know very well, in Sri Lanka, okay, most of our concrete, if I take our ready mix, for example, in say concrete, more than 90% of our concrete are S4, are at the highest class of consistency, S4. You see the S5 here, more than 220, this is not recommended. You see the small a is saying that it is very difficult to consolidate those concrete and to keep a good stability. Better to go below 220. And in Sri Lanka, we have this class of consistency. If I look, for example, our volume of concrete we produce at INSEE concrete, I would say more than 90% is this class of consistency. And more important is the with time, in Sri Lanka, we always ask 3 hours. It's very, very challenging. Okay? Now, other countries, they have a degree of compactability. For example, in Switzerland, they also use the slump test, but they use also this degree of compactability. It's very simple. You have a box, you fill it without compaction, you fill the box with concrete. After that, you vibrate the concrete with a certain vibration frequency and certain time. Okay, and you measure the slump. And the degree of compactability is the ratio between H1, the height, divided by H1 minus the slump. That is the degree of compactability. Lowest is the value, mean, higher is the slump of the concrete. It's normal. If I place this concrete, I compact it and it's not slumpy, it means already the concrete has high compactability. And also there is what we call the flow diameter. Sometimes in Sri Lanka, we use it, but we don't use the right cone. We use this cone to take the flow. Normally the cone you use for the F class, the flow diameter is smaller. This is the DIN cone. It's not the Abraham cones, it's a DIN cone. Therefore it's different. Therefore you lift the cone and you compact. You give a tap, 15 tap here, and therefore you measure the diameter. And there is also what we call self-compacting concrete. These are concrete normally. They flow and they go. You don't need to consolidate them. Therefore, there is a special test for them. They use the Abraham cones. You fill the cone, you lift the cone, but without vibration, without compaction, and you measure the slump flow. We call it slump flow. Here also you have class of consistency. You see, it's not as simple as a person can consider. Therefore, you have class of consistency, and within the class of consistency, you have the type, how you measure the consistency of your concrete. Okay? Therefore, step number 6 is the water content. Therefore, the water demand, as you probably have, is influenced by the slump requirement. You see, what is the slump I need? What is the aggregate size and shape? Now we know how to get it. The air content, we know. Type and content of cement, that will come later. What is the type and what is the content of my cement? The temperature and the admixture. These are all, they will influence the water content. Okay, now, if I take the slump, okay, as I said, very often, you need with a set of material to do this type of, experiment. But you can take this table to start with. It's a very good table. Very often I use it. It works very well. For example, if you take 150 to 200 millimeter slump for non-air, okay, if I have a concrete of 25 mm, I need to put about 200 liters of water if the maximum size of aggregate is 25. That is why very often in ready-mix operation we use super plasticizer. Therefore, we can cut by almost 20% the amount of water we add. It's okay. Therefore, you see, depending to the class of consistency, okay, and depending to the maximum size of aggregate, you have different amount of water you can use for non-air entrainment and with air entrainment. When you entrain air, because air has the ball bearing effect, you see, here I use 202 liters, here I use only 184, almost 20% less. Because in this case, I have entrained about 6% of air, and this is a ball bearing effect. It's like when you have fly ash in your concrete, you have very nice workable. That is really somehow the effect. Therefore, you can use this table also. Now, cement content, you derive the cement content knowing now the water content and knowing the water cement ratio. Now you can calculate the cement content. Very simple. Okay, you just have to divide the water that is needed for the required slump and the water cement ratio to fulfill the strength and the durability. Okay, now also a minimum cement content may be specified for the purpose of durability. We will see it probably in the next slide. Finishability. Yeah, for example, when you have a slab, very often we increase the amount of cement to improve wear resistance. And for the appearance, for vertical surface, we need to have a little bit more paste to have a very nice finishing. Okay. Therefore, also excessive high cement content should be avoided for economy. 60% of raw material cost in cubic meter of concrete is a cement cost. Therefore, do not abuse. Don't put too much cement. This is not good, because adverse effect. Because if you add more cement of hydration and so on, okay? That is why if you produce a concrete above 40 megapascal, normally nobody will do it with OPC. If you do it with OPC, you can have adverse effect, heat, shrinkage, and so on. Or if people use OPC, they will add flash somehow, okay? Now, also there is some recommendation, for example, Portland Cement Association, if it is frost resistant, this is not our case, or when it is underwater concrete. Underwater concrete, you need to have more than 390 kg of cement. Or if you are really for finishability and durability in flat work, you see, for example, if I take the case of Sri Lanka with 19 mm, 20 millimeter, 22 millimeter, we cannot go, okay, below 320. We cannot go below 320. That is exactly how it is the case in Sri Lanka. We have even more than that. Now, the type of cement. Here again, it's really important that we discuss about the type of cement, because when you talk about type of cement, you know, cement is not only compressive strength. Of course, the cement is responsible, is the binder, is really the binder, is the glue of concrete. But cement is more than that. Cement can provide you low heat, can provide you better workability, can provide you better economy, can provide you a longer strength, better durability. Okay, you have type of cement that can give you this type of feature, advantage, and benefit that you cannot get, for example, from a pure OPC. You cannot get it. If I have to do a foundation, I go pure OPC, I will have full of thermal cracking. For example, just a very simple example. Okay, or if I'm in a sulfate environment, I have OPC and my C3A is above 5%, I can have sulfate attack. For example, this is why I say it's very important here that the type of cement, this is why the next webinar I will discuss more on the type of cement, that you can make the link. As I said, it's not about the megapascal. If it is only a question of megapascal, the challenge is very simple. Very easy to achieve 25 megapascal or 40 megapascal. This is not a big challenge. Now, I have to speed up. Now, the cement type. Here again, you see, in the cement type, very often we use fly ash, we use silica fume, we use slag, okay, we use limestone, we use metakaolin, we use pozzolanic material. You see, they are all some kind of pozzolanic materials. Some are latent, some are not latent, some have some seeding effect, filler seeding effect like limestone powders, okay? These are all, when you integrate them in the right cement technology, they can fulfill a specific need for the engineers. That is really important to consider. And also the relationship between water cement ratio and compressive strength. If I use silica fume, or if I use slag, or if I use flash, if I look my relation, compressive strength and water cement ratio, you will see easily, you can do it, that blended cement, for example, they will develop much more strength than OPC, for example. If I look 28 days, 56 days, Okay, that is important for me as an engineer. Why 28 days? Okay, who will jump on the bridge at 28 days? Who will jump on the slab on 28 days? Which concrete elements are under service at 28 days? None of them. Therefore, as an engineer, I want really to fully take advantage of the intrinsic properties, of the intrinsic engineering properties of the concrete. Therefore, I should open up and say that yes, the time when you were driving cars, engine with petrol, are not the same today. Today we drive cars not with petrol, we drive with electrical batteries, we drive with hybrid. Therefore, they will drive us, but the technology is not the same. Therefore, I cannot compare, let's say this is good or this is better. No, it's just that this technology is just different. And if I'm looking for sustainability, if I'm looking for low CO2 footprint, if I want to be, let's say, a responsible citizen, responsible engineers, I have to integrate this technology when we talk about sustainability. Which product give me less impact on the environment, for example. This is something we will discuss it the next webinar. Now, these are the different mineral components that we use, for example, in Sri Lanka. Okay, high-grade calcium carbonate, high-grade limestone, fly ash from Noroccheni. This is from our own quarry, and ground slag we bring it from our operation in the region. Okay. Therefore, this what we call superior blended cement. These are for sustainable performing concrete. Okay, we will discuss it. Therefore, we have different product. Okay, and all these products you see they have received the green mark certification. Okay, and they have different value proposition. For mass pouring, for example, if you look the Lotus Tower was not developed with, for example, Rapid Flow Plus or for Marine Plus or with Sansa. Because the challenge with this project, the Lotus Tower was mass, a huge foundation. Therefore, we have value proposition, a product for this. And so on, for high workable, high durable, for concrete where water cement ratio is high, you need to have a good strength development. And this is why the Sansa is the R class for early cements, because they put too much water. And you have a very good cohesiveness. For example, this is Marine Plus, this is for high strengths. That is for high performance concrete. That's why you see the value proposition is different, therefore we have different products. We see as an engineers now, you understand, it's like if I have a headache, I mean, look, I just give some, if I go to the pharmacy, you can buy Panadol, but you can buy Panadol Extra. Depending to which level, how is your headache, how is your, that is why it's not only one fit all. It's not that one OPC fit all, no. You have exposure condition. Therefore, as an engineer, I want you to keep this in mind. Therefore, you have today a panoply of solution, and you need to take this into consideration. Otherwise, you miss something that is important, is are you able to guarantee, for example, that up to 50 years, you will not have a certain deterioration due to a condition of exposure, okay, that will affect the integrity of your structure. I mean, there are several cases, Recently, you know about the cases from Italy, in Genoa. The bridge that collapsed, now they built it they inaugurated less than 4-5 weeks ago. They inaugurated the new bridge, okay, and therefore, more than 40 people died. This was built with OPC. I say expected intended service life more than 50 years, and this bridge collapsed before 50 years. Is it the compressive strength? No, it's not the compressive strength. It has enough compressive strength. It collapsed because it was marine. You have the Mediterranean Sea. You have the chloride. And reinforcement. If you remove the reinforcement, that is the weak point of concrete. In tension, concrete is weak. That is exactly what happened. Now, admixtures, you can use different type of concrete admixtures. You can use water reducer, you can use superplasticizer, you can use accelerator, but keep in mind, as I said, you have for the chloride content, you need to fulfill a certain limit to take into consideration. That is, I would like that you keep this in mind, that chloride is something we should avoid when the concrete is reinforced. It's okay? Therefore, it will be, the information is given by the supplier. He will tell you, with my product, if you use 1%, you can reduce up to 20% your water. That is given. You don't have to invent that. Okay. Now, you see, last step. You see, we have discussed how to get the cement, we have discussed how to get the water, we have discussed about the air, we have discussed about the coarse aggregate. If I know the mass, I know the density of this, I know now the volume. And I know that I need 1 cubic meter. Therefore, I need 1,000 liter. Therefore, 1,000 liter is mean I should fill what is remaining with the sand. Knowing the density of the sand, I multiply this by the density, I get the sand. And you have your density of your concrete. Done. This is how you get to the concrete at the end, and you will have seen for each of the steps how to get the cement, how to get the water, how to get the air, how to get the coarse aggregate, and at the end, to get 1 cubic meter, you fill what is remaining from the volume to get 1,000 liters with the sand volume. Okay? Therefore, what is important also, this mix design normally is in a saturated, superficially dry. It means your water cement ratio is the effective water cement ratio. This is the water cement ratio that will provide you a certain compressive strength. Okay? Now, very often in nature, when we get the sand is not always in a saturated but superficially dry, because sand has a certain absorption. If the sand is saturated to this absorption, but it is surface dry, this is a condition where your mix design, if you add water, this is the effective water. This is the water you calculate for your water cement ratio. But in Sri Lanka, very often, we are in this condition. We have not saturated surface dry, but the surface is not dry, is damp or wet. Okay? Therefore, it's very important that we know how much water we have on top of the absorption. In this case, we have more water than is required for the calculation of the water cement ratio. Therefore, if I have effective water cement ratio, let's say water is 160 liters, and I don't take out the water that is coming from the sand, for example, or from the coarse aggregate, I will have 160 plus, for example, 20 liters. Suddenly my water cement ratio will increase. And if my water cement ratio increases, my compressive strength will go down. Or in case, for example, it is your absorption, is you have less than the absorption. In this case, you need to add water to the full absorption. Or when it is totally dry, you need to add equal to the absorption. Now, the absorption is specific for each sand. Normally, the absorption of a sand is around 1%. If I take a sand, normally it's around 1. Therefore, if I do my moisture calculation, I got 4%, it means I have 3% more water that will come from the sand. If I take my mix design here, let's say I have 700 kilograms of sand, and I have 3% more water, this is about 20 liters. I mean my 20 liters will come on top of this. Therefore, I will have 177 liters. This is water cementation is not anymore as calculated in my mix design. It's higher. This is why it's really important. This is why very often, okay, there is a lot of kind of like complaint or on the cube test. The difference can come from there. Therefore, if I take my cube and I am not controlling well my water cement ratio, you can find some big variation. That is why very often when we design, we add a 10 megapascal on top. Now, the calculation, I mean, is very simple. It's not difficult, the calculation. And the calculation is that for the batch, you have always to take your calculated weight according to saturated superficially dry condition. After you have the moisture of your aggregate and you have the absorption. Okay, therefore you just apply a formula, very simple formula, okay, where you have to multiply the SSD condition by the difference between the moisture and the absorption. Let's say if the moisture is 4%, my absorption is 1%, is 4 minus 1 is 3. If I multiply 3 by 650. Okay? That is how you will do it. That's the same for the correction for the water. Because if I add 9 liter water, I should take it out from the mixing water. You agree with me? Otherwise, I have more water than I should put in my concrete. Okay, therefore that is somehow with this one I went through the 10 step important step to go how to design your concrete. Now the last step is to do a trial. To do a trial, you have designed it, you do a trial, you go to the lab, you mix your concrete, and you characterize with the properties you would like to assess. It's okay. For that, I have a kind of like exercise that next time we will do it together. For example, you are requested to design a reinforced concrete slab, okay, for a terrace hotel in Gold Face, and it's 200 millimeter thick, as I said. It is facing the sea water, but not in contact with the water. 25 megapascal is the 28 days specific strength. And the slump is 150 plus minus 25. And from the statistics, standard deviation is 2 megapascal, and there are 30 consecutive tests that are available. Okay, therefore, these are the specification, the condition for the specification. After that, you have your raw material. You have a coarse aggregate. You are the quality assurance, manager of this ready-mix plant, for example. You have your aggregate. It is, let's say, well-graded crush aggregate. It's a 20 millimeter nominal size of aggregate. That is the maximum size you have. The density is 2.7. The oven dry rolled bar density is 1,750. The absorption is 0.5 for this coarse aggregate. And the moisture content is 0.5. Okay? Now, the sand, it's a manufactured sand, what you have. The specific gravity is 2.7. The finest modulus is 3. This is what, when you do your sieving, you get a finest modulus of 3. The absorption is 1%. And this sand has a moisture content of 3%. Okay? Now, we use also admixtures. As a ready mix, you use super plasticizers, and the manufacturer recommends to use 1% by weight of cement to achieve 20% water reduction. And these super plasticizers is 1.1 in terms of specific gravity. You see, you have this input data. From the raw material, we have discussed it all in the presentation, and this is a condition for the design. Exposure condition, the requirement for the sense, the slump, the statistic, okay, the thickness, and it is reinforced. And that is important, is facing the sea, okay? Now, what we will do next time, you see, I have put all the steps from 1 to 12. Therefore, from the information you have got, We will calculate the concrete mix design to meet the condition and specification by following the 12 steps, okay, of the absolute volume method based on the EN 206. Okay, that is what we will do next time. I will take the first 15 minutes, 15, 20 minutes, and we will go through it, and we will somehow correct it together. It's okay, don't feel lost. You will get this presentation, we do the correction together. You will have the document with you, okay? And also, I would like also really when we are more, I say, our mobility, the mobility is easy. We can form a group of a group of 20 of the crowd. You can come to eye. I can do with you another case. You design it. We design it together. A totally different case. You can bring a case if you want, and we do the concrete together. In our wet lab. Therefore, just to really somehow walk the talk. Let's put it like that. That you will get used. Always is good. Is learning by doing. You agree with me? Okay, thank you very much. I took 10 minutes more. Sorry for that. Probably I start 10 minutes late, but anyway, no problem. Therefore, if you really have, I will stop sharing. It's okay, or I don't need to stop sharing. I can just put it like this. Therefore, if you have question, please, the organizer, you can take the form again. Who is somehow doing taking the question?
Thank you, Dr. Moussa.
Sorry, Charita, sorry. Okay.
Yeah, and attendees can share their questions now in the Q&A session. At the moment, we have received two questions, one from Mr. Asanka and one from actually I cannot read his name. And from our side, Krishan will allow for Mr. Asanka to raise his question now. Okay, since Mr. Asanka is not responding, I will read his question out. His answer, his question is it bulk density or specific gravity of aggregate? What Dr. Moussa is referring?
It is the dry roded bulk density. Dry roded bulk density is not the specific gravity, no. Is the dry roded bulk density.
Okay. Thank you, sir. And Krishan, did you raise the question?
Because you know the dry roded bulk density was just what I want to say. You see, when you take a volume, let's say I take a bucket of 10 liter and I compact my aggregate. You agree with me? If I compact my aggregate, I have porosity. Yes, I have an empty space between the aggregate. See what we say? This is a bulk load density. It's a bulk density. Therefore, I weight and I divide by the volume. This is my bulk. This is like kilogram per cubic meter. It's okay.
And the other question, could you please explain what quality of cement is affected when different ingredients such as FA or SF or slag is added to cement?
Yes. I mean, really, this is why that is a very important question. It's why the next webinar I'm going to discuss really in deep about this, because these are what we call a supplementary cementitious material. supplementary cementitious material, when you talk about slag, or when you talk about fly ash, when you talk about silica fume, when you talk about pozzolan, about limestone, about the bone ore shale, about whatever, calcine clay. Okay, these are all materials, okay, that can substitute the clinker, okay, and they are participating in what you call a pozzolanic reaction, or a filling effect reaction, is a physicochemical, okay, to provide you a certain resistance. When I say resistance, compressive strength, for example. And at the same time, they also improve your permeability. But I have a presentation for that. I hope that next webinar, the participant, he will be present, but he will see exactly what we are talking about. These are really what you call mineral components or supplementary cementitious. It's a pozzolanic material, let's put it like that.
Okay, and another one, sir. How do add fly ash content to the mix design? It's by Mr. Tarindu.
How do flash?
How to add fly ash content to the mix design?
Okay, there is two different way. There is three different way even, depending to the quality of the flash. Okay, we have standards. Therefore, when the residue on the 45 micron is below 35%, you can take this flash and have a blender, blend it with finished product like with cement. Or you can take this flash, directly have a silo, like in some ready-mix operation in Sri Lanka, we can see it. People have a silo of flash, and when they mix concrete, they replace the cement by, let's say, 10-20% of the flash. You add it as you add the cement, okay? But we at INSE, we are a cement manufacturer. We produce cement. We do not bring the cement from outside. We have our own asset. We produce cement. Therefore, we have a grinder. We grind the flash. We intergrind it with a clinker. Okay. For example, we have product up to 30% flash. We will take the flash, pump it to the mill with the gypsum. We intergrind them. We reduce them to very fine material below 45 micron, and after that we pump them to the silo, and this is a finished product. Therefore, the flash is intimately mixed with the cement. I mean, with the clinker, with the gypsum, and so on. There's different way to bring it, but we prefer, in terms of quality control, that the ready-mix person control only one material. That is why a finished product where the flash is already in is the cement with flash cement. Like according to our 1247 SLSI, we have a hydraulic blended cement, we have a flash type. This type of product is exactly how we produce. Okay.
And again, we have another 3 questions.
Yes, please.
Mr. Nithusaran is asking, what happened to concrete strength if local sand is used in mix instead of river sand?
Yeah. Yes, this is a very good question, because
I mean, he is asking whether what will happen to the.
Sorry, I don't get the last part of the question.
So now he is asking whether what will happen to the strength of concrete with reference to the local sand or river sand.
Yes.
Yeah.
Okay. I mean, here again, the question, because if it is a real well-controlled manufactured sand, the compressive strength will be equal or even better. Okay, when you use this quarry dust or manufactured sand, but you know, in the market very often you find very inconsistent quality of this slow-moving product, this quarry dust. And in this case, yes, you can have a very high inconsistency in terms of strengths. This is why first things is very important that you control the input material, you control the grading, you control the fines content, you know, of this, let's say, alternative sand to river sand. Alternative sand to river sand. I have a presentation about this type of, let's say, alternative sand to river sand. This could be a presentation I can share with also the platform, I say the professional, you know, if you are interested. But to answer to like, there is not only one answer to that. You see what I mean? Therefore, it depends very much on the quality of this sand you are using. Because if this sand has a lot of dust, a lot of particles below 75 micron, okay, and very, very bad shape, he will have difficulty even to mix that concrete. He will add too much water. He will have bleeding, suddenly he will get at the end with problem with strength. But doesn't mean that, this is why I say when you have issue, you see some implication, always it's important to develop solution. And the solution is what I said at the very beginning of my presentation. When we talk about concrete mix design, we are not always, I mean, as engineers, we should accept that we are going to be more and more challenged, okay, with scarcity of sound, very sound, aggregate and sand. We should accept it. Because this is the nature, you know, the nature cannot give us more than what it can, but this is why there is a lot of alternative, and this is why we need to somehow use the right, I say, quality control, use the right, I say, investment that the people who are selling those products, you know, they make some effort to bring those products in a more consistent quality. That will be no problem. For example, if you look in the Colombo region, all the ready-mix operation, 90% plus, the produce is this type of sand that is not natural sand. These are manufactured sand. Yeah, therefore, we produce excellent concrete with this type of sand. This is not a problem. If you remember what I said at the very beginning of my presentation, the technology content is very important. It's very important. Very often I see colleagues, they jump very fast, they jump to the conclusion, the cement is not good, the aggregate is not good, the sand, no. Really, the technology that is used when they produce these different raw materials has a big impact, okay, on the final quality of your concrete. Okay, if I have answered that question?
Yes, sir. Now we have a live attendee from the Zoom screen. Krishan, will you allow him to talk? Mr. Janit? Mr. Janit, could you raise your question? Okay, thank you, Dr. Moussa. And since the question amount is getting higher and high, we will promise you to answer all these questions by the next session. I mean the second session of this workshop. And my colleague, Mr. Deshan, will present the balance part of the workshop. I mean the introduction to the next presentations and final things. Mr. Deshan, please.
Thank you, Charita. Good evening, everyone. I am Deshan Gamagi, Vice President of Vice President of Young Professionals Forum, ACSL. Thank you all. Thank you again all for the fruitful interaction during the Q&A session. As promised by Charita, any other important question raised by you will be directed to Dr. Moussa and will be taken into the discussion at our next session. So our next session will be on cement and cementatious materials, and this is scheduled to be held on 8th October 2020. And first part of the next session will be dedicated to discuss the case study, the example on mixed design calculation given by Dr. Moussa today. So your participation and interaction at the next session is also highly appreciated. We will email you the exact time and link for the registration in due course. And further, I would like to take this opportunity to invite you for another event, a technical conference organized by Sri Lanka National Committee on Large Dams in collaboration with Young Professionals Forum of ACSL. It will be held on 29th September 2020 from 8:30 a.m. to 3:30 p.m. at INSEE I2I Center, Paliagoda. The theme of this conference is Resilient Dams for Future. We will send the link to register via email, so anyone interested can get registered through that link and participate. Thank you all again, and I will invite Charita Handagala, President of YPF, to conduct the vote of thanks.
Thank you, Deshan. Finally, we came to the end of the session, actually the session 1 of the workshop on concrete mix design and cement use. And first, I would like to thank Dr. Moussa for the fantastic knowledge sharing presentation, and for INSEE team for the partnership with the event, and my colleagues from Young Professional Forum, ACSL, and for the Young Professional Forum, all young members below 40 actually can join their hands with the Young Professional Forum with by applying their by forwarding their applications to the Secretary YPF. And thank you all for the participation, and we will meet with next much better knowledge sharing presentation, of course with INSEE at 8th October 2020. And thank you. Good night to you all.
Thank you very much. Have a nice evening, everybody.